Hey class, and welcome back. We're going to now continue our investigation of forces in motion as we move into chapter 5, and we're going to be talking about a topic known as uniform circular motion. And as the name implies, we're looking at things that are moving around in a circular pattern uniformly, meaning at a constant speed. So we're going to start here. Later on, we'll add in things that are moving non-uniformly through a circular path, if they're accelerating around a turn and so on. But for now, we're going to just start with uniform circular motion and look at the forces involved. You know, if something's going around in a circle at a constant speed, you think that it would not be accelerating because it has a constant speed, but it actually is accelerating since it's constantly changing direction. So interesting. I wonder how we could describe that acceleration. These are the kinds of things we're going to be jumping into. So here we go. Let's go ahead and start by defining what is uniform circular motion. Well, uniform circular motion, as the name implies, is an object moving in a circle, guess what? Uniformly, all right? It's moving in a circular path at a constant speed. So here's an example of a kid with a little flyer plane swinging it around, or I brought my fancy little ball on a string, so if I get this swinging at a constant speed, it would be undergoing uniform circular motion. This has been one of my favorite physics demonstration devices. It actually used to hang in my garage to tell me how far to pull forward my car. And then we moved and it became a physics demonstration device. Good times. Good story, huh? All right, so let's go ahead and define some more things about uniform circular motion and then jump into some of these slightly confusing topics. So if you had an object going around in a circular motion here, you could define how fast it's going based on two things. One, the size of the circle, or its radius, and two, something known as the period. So when you see capital T here, that represents the period, and that's the time it takes for an object to complete one full revolution. So the speed then, if it's moving at a constant speed, is just going to be equal to the circumference of the circle, 2 pi r, divided by that time it takes to complete one cycle, T, known as the period. All right, one other thing I just wanted to define for you quickly. So T is the period. That's the time it takes to complete one full revolution. All right, you'll sometimes also see or deal with something known as the frequency of an object. The frequency is the inverse of the period. The frequency is the number of cycles that can be completed in a given period of time. If you define it as the number of cycles per 1 second, then you're going to be using units known as hertz. So if you ever hear of units of hertz, it's actually number of cycles per 1 second. All right, so the period is equal to 1 over the frequency, and so that enables us then to take and substitute this frequency into our speed equation seen up here. And if we do that, what we find is that the speed of an object moving in uniform circular motion is equal to 2 times pi times the radius and then multiplied by the frequency. So you can either calculate it using the period and the radius or calculate it using the radius and the frequency, since, as we just learned, frequency and period are directly related to one another. All right, so let's just do a quick kind of simple calculation example. Make sure you guys understand this stuff. So imagine you go to get your tires balanced. All right, let's say your tires have a radius of 0.29 meters is the radius. All right, so it's almost 0.6 meters across. They're being rotated on this device. They get them spinning so that they're rotating at 830 revolutions per minute. I want you to tell me how fast is the outer edge of your tire moving as it rotates at 830 revolutions per minute. So I want you to calculate this, but I also want to ask you a quick question before you get started. What is 830 revolutions per minute? What is that even a measurement of? Is it speed? Is it period? Is it frequency? I'll give you a hint. It's one of those. All right, what do you think? Make a guess. All right, if you said frequency, boom, nailed it. All right, so that is a frequency. It's a number of cycles, in this case revolutions, in a given period of time. All right, so it's 830 revolutions per minute, which is a frequency. So to determine the speed, you can pause the video and try to solve. I'm going to continue on. To determine the speed, I decided to go ahead and convert my frequency into a period You could have just used frequency as we saw in the last slide, but I just want a little extra practice. So I took 1 and divided it by the frequency. But I noticed, look, my units that I get, it's 1.2 times 10 to the negative third minutes per revolution. Since I'm dividing, my units flip-flop, right? The minutes on bottom become on top. So that's minutes per revolution. Though since I want SI units, I'm going to have to convert that to seconds from minutes. And so I multiply by 60 to get my seconds. So the period is 0.072 seconds. Again, what does that mean? Realistically, make sure we understand that's the amount of time it takes to complete one cycle. So my tire is spinning so fast that it only takes 0.072 seconds to complete one revolution. Boy howdy. Now to figure out the speed is 2 pi r over the period. So 2 pi times our radius, which we're given, divide by the period. And so the outer edge of the tire is moving at approximately 25 meters per second. All right, pretty good. Boxworthy, yes. All right, so a couple of thought questions for you as we move on with these concepts. Imagine you're in a car, all right? I don't know if when you were a kid you used to play corners, but I was one of 3, and so we had 3 across the back seat regularly, and we would play a game we called corners, which means you go around a turn, and everybody just allows their body to be pushed outward, and whoever's on the very outside gets smashed against the door, right? I don't know if you ever played corners, but we did. You just make sure the door is locked if you ever try it. So anyway. It always was for us. So anyway, okay, good story. All right, so my question to you all is, say you go ahead, you make a left turn, you feel as though you're being pushed to the right. Is there a force pushing you to the right? 2 questions, really. One, is there a force pushing you to the right? And the second question is, if so, what is that force? If not, why not? All right, so think about it. Tell me what you think. Dun, 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 dun. Drum roll. The correct answer, boom, no, there is no force. Oh, I bet a lot of you said yes. Yeah, what is right? A lot of people probably said yes. A lot of you are probably thinking, oh yeah, there's that centripetal, centrifugal, or something like that force pushing me outward, right? That's why I feel that. No, wrong. So what? Yeah, okay, there might be a force from your sibling pushing against you, especially, you know, if it's like my sister, she would push against the door to add a little bonus force. But if we ignore that, there's no actual force pushing you outward. So my second question then is, what, right? Why? Why do you feel as though you're being smushed up against that door? Why does it feel as though you're being thrown to the right? And I'll give you a one-word answer. It's a pretty tricky and confusing concept, but the single answer is inertia. All right, this is really confusing. So if you're moving straight and you're turning to the right, or let's do it this way. You're moving up and you're going to turn, in this case, to the left, actually, right? That's what we said, okay? If you're moving up, your inertia wants to keep going upward, all right? If you were moving up just before you took the turn, and if the car were suddenly to disappear, you would just keep moving in the upward direction, right? You would just keep going upward. Maybe we'll use the tennis ball to represent you, okay? You're moving up, you're gonna turn to the right. So as you're moving up and the car starts to force you to turn to the right, like this, your inertia makes you want to keep going, and you feel slammed against the side because the car is making you turn with it, all right? So you want to keep going, but the car is forcing you to go to the left with it, all right? So your inertia makes you want to keep going, the car gets in the way, and so you feel as though you're being pushed against the edge of the car. Inertia is why you feel that, all right? So with that in mind, okay, then it seems like our feelings are messing with us. If we feel like we're being pushed outward, but we're not actually being pushed outward, then what is it that we're even feeling? When it comes to motion, what do we feel? All right? What do you think? Well, the correct answer is we feel acceleration. All right? What we feel is when we have an acceleration, not velocity. That's a common misconception. A lot of people are like, oh yeah, we feel velocity. You know, I get going fast and I feel it, no problem. But think about that. Really? Have you ever been in an airplane before? All right? Did you know that you're cruising at hundreds of miles or meters per second? Does it feel like you're moving at all? You could close your eyes and feel the same as if you're sitting in a stationary vehicle on the ground, right? So it's the acceleration that you feel. And a tricky thing about the feeling of acceleration, all right? The feeling of acceleration that we get a lot of times is exactly opposite of our true acceleration. Think about it. If you take off, if you're sitting in a car and you start going super fast, right? What does it feel like? Whoa, you feel like you're being thrown backwards. You're accelerating forward, you feel thrown backwards. All right, same thing when you stop, right? You hit the brakes, you feel like you're being thrown forward, but you're accelerating backwards. So it's really your inertia that you tend to feel, right? And it's the acceleration that's almost exactly opposite of that inertia. All right, so again, acceleration is all we can feel, and a lot of times it's a little bit misleading because what we feel is a sense of acceleration in the opposite direction of our true acceleration. So imagine if you're in a bumper car, you hit a wall. I've done that before in bumper cars before. You feel as though you're being thrown forward while your acceleration is actually in the backwards direction. All right, so don't be fooled. This is a common misconception. What this means, though, is you're always going to feel an acceleration in the opposite direction of your true acceleration. All right, so let's go back to this idea of uniform circular motion. If we have something moving in uniform circular motion, all right, keep in mind what this means is that it's moving at a constant speed. And I emphasize this a couple times. It's moving at a constant speed, but not a constant velocity. Why not? Well, as this diagram shows you, its direction of that velocity vector is constantly changing. And so if its direction is changing, that means it's experiencing an acceleration. And as we learned back in chapter 4, what that means is if the speed stays constant, but it has a change in acceleration, then that means if the speed stays constant and if it has a change in velocity, that means that the acceleration must be perpendicular to the velocity. So what you see as shown here is if you have a constantly changing direction but a constant speed for your velocity vector, you're going to have an inward pointing acceleration. And you'll see this acceleration expressed two different ways. You'll see it as you see here, written as a radial acceleration. You'll also see it written as A with a C subscript for centripetal acceleration. I'm actually going to show you both of those throughout the course of this lecture so you don't get confused when you see the opposite one later. There's some slight differences between radial acceleration and centripetal acceleration, which we'll talk about later in the semester, but for now you can consider them to be interchangeable for chapter 6. All right, so if you have something in uniform circular motion, what that means is there's some inward pointing acceleration that you can call either a centripetal acceleration or a radial acceleration. Both terms are okay, but it's perpendicular to the velocity vector, so it's directly inward. So for this, while I'm spinning my ball around on the string, that means that it's acting in the direction of this string. All right, so this inward pointing acceleration, the center-directed acceleration, is known as a centripetal acceleration, acting radially inward. So you see it written as either centripetal acceleration or radial acceleration. All right, and so it's caused by some centripetal force that's also pointing inward. Now don't get confused. It's not some magical special force known as a centripetal force that comes from nowhere, okay? No, all centripetal forces are always supplied by something. All right, so again, back to my tennis ball on a string. As I'm swinging this thing around, what is supplying the centripetal force? It has a centripetal force, it has a centripetal acceleration. We've already established that. Where does it come from? Well, it comes from the string. The tension in the string gives it that inward pointing force, that centripetal force directed towards the center of its motion. All right, so again, something must always provide that force to keep it going in its circular motion. So we call this centripetal force, and it gives rise to the centripetal acceleration. Keep in mind, a lot of times you're going to feel the exact opposite. That's a result of inertia. That's not a real force. In fact, though, because people feel it so much and associate it with circular motion, it's been given this kind of misleading name as a centrifugal force. There's no such thing as there's no such thing as a centrifugal force. It's just the name for that feeling of inertia. All right. So I don't want to hear you talk about centrifugal force. Centripetal is what we got, and it's always a result of some real force. I'm going to test you on some of this here in a minute. All right, so quick question for you all. With all this in mind, if I'm spinning this thing around in a circle, maybe I'll make this a little bigger, all right? If I'm spinning this around in a circle here, oh, just kidding, there we go. So if I'm spinning this around in a circle here, what would happen if my string suddenly broke? Let's say that while I'm spinning it, when it's right up here at a vertical position going like this, if I were to just let go, if the string were to break, what would happen? What do you think? Well, let's give it a go. Oh, okay, I just hit myself in the leg. All right, let's give it a go. Ready? We get it going, get it going. Ooh. I don't know if you saw that very well. It wasn't the most amazing demonstration on video, but if you saw what would happen, or if you guess what would happen, because of Newton's first law of motion, it would tell us it would just continue moving in an exactly straight line. So when I had it right here, moving in a circular motion, its velocity vector is pointing this direction, right? So at that instant, it would just continue moving in a perfectly horizontal manner. If I released it when it was moving downward over here, it would continue moving straight downward as well, because there's nothing providing the centripetal force. You must have centripetal force. If not, your object will continue to move in a straight line. All right? Sweet. So I told you I'd ask you a couple questions. I got a couple conceptual questions for you here. You're driving in the car. All right? As you can see, this car is going straight. It's going to be making a right turn. All right? And let's assume that this is perfectly flat ground, okay? Sometimes curves are not flat. We'll talk about that here in just a second. But out in the middle of nowhere, Nevada and other places, you have some flat curves. So if you're going straight and turning to the right on this flat curve, you're turning, you're changing the direction of your velocity vector. Therefore, there must be a centripetal force. What is generating and supplying the centripetal force? What do you think? Make a guess. Write it down. Commit. Tell your friend, okay? Well, what do you think? Guess what? It is friction force. And the craziest thing is the friction force that's generating is in the tires and is pointing in towards the center of the circle. So again, I'm going to pop back here for a second and show you on my whiteboard what I'm talking about. All right. So what I'm saying here is if we have a vehicle that's turning, all right, if we're looking at the back of the car, so here's the car. Now you get to see my beautiful artistic abilities. Okay, here's the car. It's on the road, right? And it's turning, it's going into the board, and it's going to be turning right, all right? So it's turning this direction. That means that its centripetal acceleration must be this direction. The centripetal force that's provided by some outside force must be in that direction. And so the only place that that can be is right here. So in the tires, you're going to have a force of static friction pointing inward. So again, it's pointing on the tires inward in a direction you wouldn't normally think of. Since you're driving into the board, it's going to be pointing in towards the center of your circle. And it's that generates the friction force that makes it possible for you to complete your turn. Pretty tricky. So what a lot of civil engineers do, because they know their physics, all right, is they say, okay, this is a lot of friction for these tires to need to supply. It can be risky for people trying to make these curves. All right. In fact, I've been driving in the snow around a curve at times, and I've actually not been able to make the turn because my tires were not able to supply enough centripetal force for me to complete the turn. And I one time actually slid across, bounced off a snowbank, and luckily the snowbank supplied the outside force needed for my centripetal force to change the direction of my velocity vector so I can make the turn. My wife just said that's the nerdiest statement of all time, but she hasn't heard all the lectures yet. So, but yeah, it's a little nerdy, but it's also really cool. All right. So, good. Acceleration, as you can see, it must be inward because of the circle, but you feel like you're being pushed outward. That feeling of acceleration is opposite, as we talked about earlier. Cool. So if you wanted to look at a free body diagram, as I mentioned before, you'd have the normal force going up, your weight going straight down, and then the only thing going in the x direction is the friction force supplying your centripetal force needed, supplying that centripetal or radial acceleration. Again, just to drive home, you will see this written as both radial, A rad, and A sub C, centripetal acceleration or radial acceleration. So, as we mentioned, engineers a lot of times want to try to help this out a little bit. So guess what they do? Engineers decide to bank curves. They'll take a road and they'll put it at a slight angle in order to help you out. So the question is, why does that help? Why do engineers bank roads? If you don't know what I mean, I'll have a picture here in a minute. But basically, what we're doing when we bank the curves is we'll, instead of having a nice flat road to go on, you'll have an angled road like this so that your car now is driving around a curve that's at an angle like so. So why would they do that? What do you think? Go ahead, make a guess, and in doing so, think about what is it that is able to supply your centripetal force in this new banked curve version. Well, the answer, you guessed it, is not only friction, that's still part of the story, but also now when you have a banked curve, your normal force is going to be perpendicular to the road, as always, and so a component of your normal force is going to be inward towards the center of your circle. So a component of your normal force can assist the friction in supplying your centripetal force required. All right? And so, in fact, a lot of times, banked roads are banked in such a way that in theory, you should be able to make the banked curve with zero friction between your tires, relying solely on the normal force to supply your centripetal force. But that's only at a very specific speed, which it's almost impossible to keep your car at that exact speed. So as a result, you want some friction between your tires and the road, trust me. Not to mention you can't go forward without friction. So how do we quantify this centripetal acceleration? Again, here you see it ARAD or AC. Both of those are ways of writing centripetal or radial acceleration. The way it's quantified, you can derive this from basic principles, and there's a derivation in the textbook. But I just wanted to go ahead and tell you that the centripetal force is always going to be equal to the speed at which your object is moving squared divided by the radius. So what that means is there's greater acceleration if you're going faster, and there's greater acceleration if your radius is smaller. And you can see that, right? Again, if you're swinging an object, the faster it's going, the more tension. You can feel it in the rope, and also the smaller the circle, the tighter the circle, the more tension you're going to have as well. All right, so if an object has centripetal acceleration, there must be some inward pointing net force that it's experiencing. So that inward pointing net force, since force equals mass times acceleration, that inward pointing net force is going to just be equal to mass multiplied by your centripetal acceleration, which we just said is v squared over r. So the net force that your object's experiencing must be equal to mv squared over r. Now this is a little tricky though. So far we've always been doing some of the forces in the x, some of the forces in the y. But with the uniform circular motion, the direction of that force is always changing. So now we're going to have to think of the uniform circular motion, the net force being inward towards the center. And so for something in a vertical circle like this, you're going to see in the homework it gets a little tricky. Because when you're at the top of a vertical circle, tension is down, as is the weight of the object. Whereas when you're at the bottom of the circle, the tension is up and the weight of the object is down. So you're going to have a different tension in the rope depending on whether you're at the top or the bottom of a vertical circle. And then if you're at the side, the tension's in and the weight's down. All right? So you have a different situation at each point. It's a little tricky. Cool. So going back to the banked curve idea, I want you to do a quick derivation for me. Imagine you were hired by some people who are planning to build these banked roads. They want you to be their engineer to tell them exactly what angle they ought to bank roads. But they're going to be doing all different kinds of roads across the state. And so instead of giving you numbers and you telling them one set angle, they want you to derive a general equation. All right? They want you to tell them, based on the radius of the curve and based on the recommended speed that they're going to be using on these curves, they want you to tell them what angle they should bank their turns. Now notice one thing that's not in here. Wait a second. Where's the mass of the car? Doesn't it matter if it's a sports car or a big truck or something? Well, I don't know. Let's see. Do the math, try it out, and try to come up with an equation for the angle. If you get stuck, you can leave mass in there, but I'll give you a hint. It should cancel out. All right? Give it a go. Pause, go. Okay, unpause, hopefully. All right, I'm going to continue with the solution. So let's do a free body diagram. As always, we want to start with a picture and a free body diagram. If this is our road here, it's at some angle theta, all right? We have weight going straight down, okay? And we have a normal force perpendicular to the road, and we want to bank it in such a way that it has no reliance on friction. So I'm not going to draw a friction force. All I have is normal and weight, okay? Now notice, a lot of times with ramp problems, we call the parallel to the ramp the x and perpendicular the y. In this case, I did not do that because my centripetal acceleration must be parallel to the ground in towards the center of the circle. So I called that my x direction. If you rotated your axes, that's okay, but now your acceleration needs to be broken down into x and y components. That makes it a bit trickier to solve. So instead, I decided to break my normal force into its x and y components. Its x component is normal sine theta, and its y component is normal cosine theta. All right, so if I do sum of my forces in the y direction, all I have is the normal component in the y and the weight going down, so those must be equal and opposite since I'm not accelerating in the y direction. So normal cosine theta equals mg, that's sum of the forces in the y. And in the x direction, sum of the forces equals ma. Again, where a is centripetal acceleration, which is mv squared over r. So my centripetal force equals mv squared over r. And the only force providing that is the normal sine of the angle theta. So if we look at this here, okay, cool. We have an equation with two unknowns. We don't know the normal force and we don't know the angle theta. So we can substitute and solve, right? If you do a substitution and solve, you can solve normal force is mg over cosine theta. I didn't write that out, but you could see that. If I plugged that in up here, my m's would cancel, and all I would be left with is g sine theta divided by cosine theta. Sine over cosine is tangent. Moving the g to the other side, I find that the tangent of my angle is going to be equal to v squared over rg. Notice the mass doesn't matter. You could give this to the engineers and say, hey, make your angle this angle based on the recommended speed, acceleration due to gravity, and the radius of curvature for that portion of the road. You might have done an inverse tangent of both sides. That's fine. I just left it as tangent of theta. Pretty cool, right? Another conceptual question. Again, the concepts in this chapter mess with people a lot. So another conceptual question for you, okay? So in a circus, a lot of times people are doing kind of different trapeze artist type maneuvers and things like that. One of those is when you have one person whose legs are hooked to the swing, hanging upside down and holding his friend who's hanging kind of right side up. All right? So I have a question for you. You have two options. One is, let's say that they're swinging back and forth. So in this picture, you can see they're going to be in the act of swinging. So one situation is when they're swinging back and forth, and the other situation is after they've stopped swinging and he's just holding the person straight down. In which situation is it going to be more difficult for the guy to support the person? In which case will there be more tension in the upside down person's arms? When they're stationary, hanging upside down, or when they're swinging as they hang upside down? What do you think? Which one will generate more tension in the guy's arm? Which one is going to be more difficult for him? Make your guess. Well, hopefully you said swinging. Swinging is when it's going to be more difficult. Why, you might ask? Well, because in both situations, whether swinging or stationary, his arms must support the weight of the person hanging there, right? But then when swinging, not only is he supporting the weight of the person, but at that lower position, the person has an upward needed centripetal force. So when they're swinging, not only must he support their weight, but he also must supply that needed upward centripetal acceleration, and so therefore the tension would be even larger. And you can prove that using an equation, if you would like, by doing sum of the forces as well. Okay? Tricky one. So, one last example problem for you all, and then we're going to wrap it up for chapter 6. So one thing that you've probably seen in different kind of movies, I actually had like a major nerd moment when I was watching The Martian, and I did like a quick calculation about this in my head. But one way you can generate artificial gravity, yeah, my wife was just saying in the background, I leaned over and started telling her about this calculation in the middle of the movie theater when we went to see The Martian, because I was quantifying to try to see if they really were spinning at an appropriate speed to generate artificial gravity. It was pretty good based on my quick approximations I could make. So anyway, nerd moment, sorry. I have a lot of those. Anyway, one way to generate artificial gravity is by rotating your space station, as you see in movies and things like that. So let's say that we have this cylindrical space station. This is obviously a scaled down model of it, but let's say it's a spinning space station that's very, very large. It has a radius of 1.7 meters, or sorry, 1.7 kilometers, or 1,700 meters. All right. Now let's say, I don't know why you would do this, but let's just say for the fun of it, you wanted the people inside to get some extra exercise. So you decide you want to generate 3 G's worth of gravity for the people inside. So you want 3 times the normal acceleration due to gravity on Earth to be experienced by the people in the space station. How fast must you be rotating your space station to achieve this? Pause it, try it out, and then we'll solve it together. All right, so hopefully you got a solution. All right, so let's go ahead and solve it and see if you got it. So first things first, you need to start always with a free body diagram. As you can see in our free body diagram here, the only force that this person is going to be experiencing, since they're out in space, is this inward pointing normal force, which is the centripetal force provided by the outside edge. So this is a confusing one, but as the person's sitting there, all right, the space station is going to be pushing up on them against their inertia, giving them a normal force, which is what is supplying their centripetal force. So the centripetal force, as we know, is mv squared over r, and we want that normal force to be equal to 3 times the normal gravity on Earth. So it's their mass times 3g equals mv squared over r. Once again, look at this. Boy howdy, our masses cancel out. And so to solve for our velocity, it's just going to become equal to the square root of 3rg. That's easy enough. So we plug in chug, plug in g, plug in 3, and plug in the radius of 1.7 kilometers. Do the math, and you should be spinning at a speed of 224 meters per second, which is indeed box-worthy. Yes, that seems fast, right? But again, we don't notice uniform speed, right? Just like up in an airplane, so you wouldn't even realize you're moving that quickly. Really cool way to generate artificial gravity and some fun physics. So that wraps up chapter 6. Please let me know if you have any questions, and have yourselves a box-worthy day.